Okay, so it's time for the final lecture in the school, and of course the final lecture of Fernando.
So thank you very much for keeping up with me. In the last, as I am running out of time, I will start without saying anything useless. So in the last lecture, we have seen that if we wanted to see Wilson loops in n equals 4 super-Yang mills, the natural Wilson loop to study was a Wilson loop of this form with coupling to the scalars. Then, towards the end of the lectures, we have seen I introduce the ADS-CFT duality, and the ADS-CFT duality gives a prescription to compute Wilson loops at strong coupling in the planar limit. And remember that the planar limit was the number of colors very large with this combination called lambda keeping fixed. So basically, in that limit, this Wilson loop in the planar limit will be a function of lambda, and the ADS-CFT duality allows us to compute this omega of lambda for very large values of lambda. On the other hand, perturbation theory will allow us to compute this just by expanding in powers of g for small values of lambda as a perturbation expansion. And today I will show you how these ideas work with a very specific example, and we will try to make an interpolation between weak coupling results and between strong coupling results. But in the way I will explain you how to compute Wilson loops at a strong coupling with the ADS-CFT duality and a weak coupling with perturbation theory. So these are techniques that are useful for a lot of things that you may want to work on. Remember that the prescription in the ADS-CFT duality was the following. So we had just a purely geometrical problem, and the problem was the following. You start with ADS5 in Poincare coordinates. So ds square is equal to 1 over c squared dx4 square plus dz square. Is this big enough, or are the indices too small? Is enough? Okay. Then what we needed to consider was the boundary of this space, located at z equals 0. In the boundary is where these 4 coordinates live. Then you need to draw the Wilson loop, right, in the boundary. And then you need to consider the minimal surface that ends at the Wilson loop. The radial coordinate of ADS is increases in this direction. And then the prescription, what I have written down the last lecture, was that the expectation value of the Wilson loop for large values of lambda was given by square root of lambda over 2 pi times the minimal surface, the area of the minimal surface. Somebody asked me why exactly this factor. In string theory, like ADS-CFT duality tells you to compute something like e to the minus s, but the action is proportional to the string tension, and the ADS-CFT dictionary tells us that the string tension is exactly square root of lambda over 2 pi. So that is what ADS-CFT tells us. Note that we are not doing minimal surfaces in flat space. If we were, this wouldn't need to enter towards larger values of z. The thing is that because of this 1 over z squared factor, it is very convenient so to have like small areas to enter as fast as possible into the bulk, into higher values of z. But of course, the worksheet, the surface has to end on the loop, so I have to come back at some point. I have cheated you a little bit, and you haven't noticed, and that's nice. But actually, this area is not finite. So if you would do this computation, you would get infinity here. Lambda is large, so you would get e to the minus infinity, and that's 0. So it's not a very nice result. This is divergent because this 1 over set square factor. But we know that Wilson loops are divergent, right? Because we have seen UV divergences. And if the ADS-CFT duality is going to be a real duality, we should get infinity while infinity, right? So that is fine. Now, what happens here is that you can actually subtract the divergence. So this divergence, due to the fact that when set is very close to 0, you can have a divergence. And what you do, we will compute the area of this surface, but not up to set equals 0, but up to, and this is some plane, and this is the plane set equals epsilon. So we are cutting, and sorry, my artistic, I am not really an artist. So we are cutting the segment from theta equals to epsilon to theta equals 0. Is it clear what I am doing? So I am cutting this little piece. So the surface would reach set equals 0, but I don't let it reach set equals 0. When computing the area, I will cut it at set equals infinity. Is okay? Now, naively, or at least you can see from the pictures, the area of that will be proportional to the length of the volume, right? To the length of the loop. Because you have like epsilon here in this dimension, and then you have the length of the loop. So we expect this divergence, this piece in pink, to be like the length of the loop divided by epsilon, or something like that, or at least proportional to this. So actually the prescription is the following. So the expectation value, the finite expectation value of the Wilson loop is a square root of lambda over 2 pi times the minimal surface, but where you may have to subtract, and in general you will have to subtract the piece, the divergent piece, which is proportional to the length of the loop. Questions? Yes?
So yesterday you said that for the supersymmetric Wilson loop, you don't have this divergence.
That's true. Yes, that's an acute observation. Acute, yeah. That's a nice observation, actually. The thing is that the prescription by Maldacena actually tells you to compute the minimal surface of this, and then you have to subtract another minimal surface. And subtracting this minimal surface is equivalent to subtracting this. So it is equivalent to that, to this, the ADS-CFT duality. So what I am saying, indeed, is that what is dual to this supersymmetric Wilson loop is not this first quantity, but this one here. So that's all what I am saying. Yeah. Any other questions? Very good. So let's now learn how to compute Wilson loops at a strong coupling. If you want to compute Wilson loops at a strong coupling, we have seen that we need to compute minimal surfaces. So how do we compute minimal surfaces? And that's the first half of today's lecture. So if you want, so the first step is how to find minimal surfaces. Minimal surfaces. Now, if in a string theory there is an action that measures, remember that if you have a particle, the action of a particle is proportional to the length of the path, and your action exactly measures the length of the path, and that's what you want to minimize, right? Now, in a string theory, we have like the two-dimensional analog of that, and what we have to consider is the action that measures the area of this worldsheet. That is called the Nambu-Goto action. And the Nambu-Goto action reads as follows, and I will explain precisely by what I mean by everything in this formula. Here, sigma 1 and sigma 2 are coordinates on this surface. So if you have your loop, your surface, sorry. Oops, I shouldn't have erased the metric. But okay. So if you have z equals 0 here, you have your loop, and you have here the surface, then basically sigma 1 and sigma 2 are coordinates along this surface and parameterize what point at the surface you are looking at. Then you have to put the square root of the determinant in the coordinates AB, and these AB are 1 or 2 and are basically this sigma 1 or sigma 2. Then you have to multiply by g mu nu. This is the ADS metric. And then dA of x mu, dB of x nu, where these run over the 5 coordinates, or over the all coordinates of ADS. So basically these derivatives are derivatives with respect to sigma 1, sigma 1. So you make a 2 by 2 matrix. The first element is D1, D1. The second is like D1, D2. Then here you have D2, D1, and then D2, D2. Is that clear? And you take the determinant of that matrix. Now, we will make some easy choices just to simplify our lives. What we will do is the following. So imagine that we have this plane. It looks better here somehow in my notes. And let's put here a coordinate x1, here a coordinate x2. Sorry. I don't know why it doesn't look three-dimensional in the blackboard. It looks three-dimensional in my notes. Yeah. So this is x2, and the z direction is like that. This is x1. Then we have the loop, like that lives in the x1, x2 plane, and then the surface that can extend towards the bulk. This is a particular case. In general, you would have x1, x2, x3, x4, but for today, it is enough with considering just this. So the metric, remember, is just the ADS3 metric, and it's just 1 over z square, dz square plus dx1 square plus dx2 square. So this is the metric. Is it clear? Furthermore, we will parameterize a point in the surface by its projection to the x1 and x2 plane. So the way you do that is by choosing x1 equals to sigma 1 and x2 equals to sigma 2. Right? So what I am saying is like a point here would have coordinates, these coordinates. Is it clear? You can always parameterize the surface by its projection. I am assuming that it doesn't self-intersect or anything like that. Then z will be a generic function that we will have to find of x1 and x2. So this means that we parameterize the surface, by its projection. Yeah, sorry, that to the x1, x2 plane. Is it clear what I mean? Yeah. Okay, very good. So now, with this choice, we come to this action here. So, for instance, we will have, well, I don't know how much detail you want me to, well, let's go into, like, painfully detail. Sorry for people who knows all that. So this determinant that I had, so now sigma 1 and sigma 2 are simply dx1, dx2. And then you have this determinant, and this determinant looks something like 1 over z squared. Then you need to take the one derivative of the three coordinates. So when you take d1 of dx2 is 0, but d1 of x1 is 1, right? So what you get in the first element is d1 of z plus 1 square. In the second element, you get, well, this 1 over z squared is like overall. It's to the fourth because it's the determinant. Then here you have d1z, d2z, d2z. Here you have exactly the same, so it has to be symmetric. And here you have the same, but with d2. Is it clear? So you take this determinant, you take the square root, and then you find, finally, this Nambu-Goto action. Can I erase this? Or is it too quick? Well, I just wait too. I drink water. So this is equal to this. So you obtain simply 1 over z squared times the square root of 1 plus d1 of z squared plus d2z squared. This is very nice. Actually, what I just have written down is the Nambu-Goto action with this parametrization for any minimal surface in a DS3. So, like, if you want to solve that problem, this is all what you need. Now, what we need to do, what we mean by minimal surface, a minimal surface is a surface that satisfies the equations of motion, right? So, what you need to do from this action, you do the Euler-Lagrange equations, and you have some equations of motion. This you deduce from this action, and then you should satisfy some boundary conditions. And the boundary conditions are that z as a function of x1 and x2 is equal to 0 at the loop. Oops. And that's the hard part. The equations of motion are not very nice because of the square root, but the hard part is that the boundary conditions may be hard to satisfy. So you have some equations of motion plus some boundary conditions. And the boundary conditions are that z vanishes if x1 and x2 are along the loop. Are there any questions? Is it clear? Oh, yes? Shouldn't be? That's a very good observation. Yes, yes. If you are powerful enough to solve this at epsilon, yes. I am not powerful enough, so I will put 0. But that is a very good observation. So, and you will see what we will do in 5 minutes. But that's, yeah, it should be epsilon if you are like very powerful. Yeah. Actually, indeed, we will need to introduce that cutoff later on. Okay, very good. So now let's focus in a very simple problem, or at least like the simplest problem that we could have at strong coupling, and it's the case in which this loop is the circular Wilson loop. I drew it almost circularly. So I wouldn't have to redraw. So if the loop is circular, we will imagine that this function here is at a distance capital R from the origin. So this loop satisfies that x1 square plus x2 square is equal to R square, where R is the radius of the loop. So now the boundary conditions are that Z should be 0 if x1 square plus x2 square is equal to 0. With these things, actually, there aren't really first principles sometimes to solve these minimal surfaces problems, so you should try luck. You should try some ansatz, and then, like, you know, if you get it, you get it, and if you don't get it, you don't. There is not much to say. Now, however, here, it is not too hard. Let's see why. So, let's call this x1 squared plus x2 squared equals to R squared. We introduce polar coordinates. So it's kind of reasonable, because of the symmetries of the problem, that this set will be a function of R only, right? It also has to vanish if little r is equal to big R, right? Because of the boundary conditions. So we could put some ansatz in which this is alpha, and then equals to, let's say, well, I write it in this way, R squared minus R squared to the beta. Can you tell me what the power of beta, what this beta power should be and why? Let's say that I tell you that the solution has this form. Can we understand what is beta? Sorry? Okay. Z is a distance, right? R squared is a distance squared, and also this one. So this should be 1/2. Then you put something like this, you put it into the equations of motion, and the equations of motion are proportional to alpha squared minus 1, so you put alpha to 1. And this is the minimal surface for the Wilson loop, for the circular Wilson loop. So it's just like a nice half hemisphere. It's just a hemisphere. Very good. So now we need to compute the area. So if we want to compute the area, all what we need to do is to take this classical solution and plug it into the Nambu-Goto action, right? That is what to compute the area is. We do that. And what we get is the following. So it's really very simple. So the minimal area is equal to the Nambu-Goto action, where you plug this classical solution, the minimal surface, and this is the integral along the circle, right, dx1, dx2, and you have R over R squared minus x1 squared minus x2 squared to the 3/2. Now let's use polar coordinates, and this is 2 pi. Let's write it here. This is equal to 2 pi times the integral between 0 and capital R of R dr. This 2 pi, of course, is because the angular integration, and this is R over R squared minus little r squared to the 3/2. Questions? Good. Now, of course, as you notice already, this is divergent. This integral is divergent. The reason for that is that we put boundary conditions at z equals 0, not at z equals epsilon. So what we will do now, we will integrate. So what we say is that we integrate this But we don't integrate it from 0 to capital R. We integrate it only up to z equals to epsilon. So we require that z is bigger or equal than epsilon. We come here, and we see that this implies, of course, that little r is bigger or equal than the square root, actually smaller or equal, yeah, r squared minus epsilon squared. And at first order in epsilon, that means that we integrate r between 0 and capital R minus epsilon squared over 2r. And that this epsilon is our cutoff. So when epsilon goes to 0, we integrate up to r, but if epsilon is different from 0, we integrate it up to epsilon squared minus 2r. Epsilon. R minus epsilon squared over 2r. So this limit of integration now, here, will be changed to this. We just do the integral, we take the the epsilon to 0 limit, and we get that this is equal to 2 pi r over epsilon minus 2 pi plus something of order epsilon. This is very beautiful because we obtain that the divergent piece is exactly proportional to the length of the circular Wilson loop. Actually, I got exactly 2 pi r. And the finite piece is this minus 2 pi. So, the ADS-CFT prediction is the following. What the ADS-CFT is telling me is that at a strong coupling, we get that the expectation value of the circular Wilson loop, and that's a circle, is equal to e to minus square root of lambda over 2 pi times minus 2 pi from there. And this is simply e to the square root of lambda. You know, with a precise factor. Not 2, not 1/2, e to the square root of lambda. So this is the prediction from the ADS-CFT duality for the strong coupling limit of the expectation value of the circular Wilson loop. So this is nice prediction. So I just did this computation so you see how different the technology of the ADS-CFT duality is to perturbation theory. But you know, we have done all the computation. This is in a paper by Maldacena and Corrado, and we have seen another people, and we have seen all the paper in like 10 minutes. So this is a nice computation. Okay, so any questions about this? Yes?
How would you explain the fact that after subtracting the divergence, you obtained a negative area?
Yeah, you don't have to explain that. But it's a nice observation. Indeed. So like here, the area looks like always positive, and you are used to the fact that it's always positive. And in a sense it is, because it's like infinity minus 1, right? But indeed, it's a very good observation that the finite piece doesn't have to be positive. Very good. Yeah, thanks. So exactly. So here we see an example that once the area is positive because it's like infinite, but then the finite piece doesn't have to be positive. And that's a feature of areas in ADS. It happens, actually. Once you subtract the divergent piece, it can be positive or negative. Very good. So record this in your notes, because we will try to see it again. Now, in the last part of these lectures, let's try to compute the expectation value of this Wilson loop at weak coupling. And let's see what we get. I promise purely Blackboard talks, but lectures, but towards the end I will use the computer for 2 minutes. But I think I will, for some of you who doesn't know, I will teach you the most important things of these lectures, that is to use a very nice site in internet. Okay, we will see. So remember that the expectation value of any Wilson loop in n equals 4 was equal, well, to this 1 over n, the expectation value of trace of p of the exponential, it's long, eh? Of I, of g, of the integral, of a mu, x dot mu, plus I x psi 1 dt. And at first order, in perturbation theory, this was equal to 1 minus g squared n. Remember that g squared n is what we call it lambda over 8 pi squared, and then we have an integral between 0 and 2 pi of dt1 of the integral between now t1 and 2 pi, because we have the path ordered, of dt2, and then x dot of t1 dot x dot of t2 minus the same combination x dot. Let me put 1 and x dot 2. Just, you understand what I mean. I mean x dot at t1 and x dot at t2. Then over xt1 minus xt2 squared, plus, etc. Now, for the circular Wilson loop, how we parameterize the loop is by telling that x as a function of t is equal to the radius times cosine of t, sine of t, 0, 0, so it moves only in 2 dimensions. And from this you can compute x dot of t, and this is r minus sine of t, cosine of t, 0, 0. Now something pretty nice happens, and if you take these expressions, right, and you replace the expressions here just for this propagator, just for this expression, you can do it as an exercise. You get minus 1/2. You get a constant. It's kind of remarkable. Like, you know, this in principle will be a function of t1 and t2, right? But actually exactly this combination is just a constant. This is just for this Wilson loop, for the circular Wilson loop. Can I erase this parametrization? So, what we get, at least at this order in perturbation theory, is that the expectation value, and let me write it in a suggestive form, of the circular Wilson loop is equal to 1 plus, because this minus cancels this minus. This is lambda, right? And 2 times 8 pi squared, we get lambda over 16 pi squared. And then we get a factor that comes just from this integration. And this is the integration between, it's just the integration of 1, because we have taken the minus 1/2. And of course, this integration is the integration, like if we didn't have this t1, it would be the integration between 0 and 2 pi times the integration between 0 and 2 pi, and that would be 4 pi squared. As we have this t1, we have half of that integration. It's very, very easy to see. So, from the integration region, we have 2 pi squared over 2 factorial. Just this. Very good. Let's go on, because now we are happy that, you know, at 2 loops it was like, at 1 loop it was so easy. So at maybe at the next order, at 2 loops, it's very easy too. And here, you know, you need some people helping you. Because diagrammatically, remember that at 1 loop, the diagram we had, and let me erase this. No, I don't want to erase this. Remember that at 1 loop, we started with 1, right? Plus the diagram for the gluon, plus the diagram for the scalar, right? Now, we are not talking about anymore about, you know, CC pure QED. We are talking about n equals 4 super Yanimals with a lot of fields. So, at the next order, you have these sort of diagrams. So, you have this diagram here. Actually, let me draw them like that. Then you have like these diagrams. You have these diagrams. But you have a lot of other diagrams too, because in the Lagrangian, you have new vertices. So, for instance, a diagram that you have is this one. Another diagram that you have is this one. Another diagram that you have is this one. Another diagram that you have, and I will stop now because I have like 15 minutes only. So, is this one, and so on. So we have a lot of diagrams where we have something interesting happening in the bulk. Now, there is smart people in the community, not me, but Zarembo and Semenov, so I am not good enough to compute these things. But they were very brave, and they have computed all these diagrams, and it turns out that all these diagrams add up to 0. So they just found like an amazing cancellation going on at 2 loops, and then it turns out that all we have at 2 loops is just this. These diagrams, by the way, and that's why I drew like that, are sometimes called rainbow diagrams or ladder diagrams. So at 2 loops, they have shown that the only diagrams that contribute are these guys here. And these diagrams, are very easy to consider and very easy to compute because this propagator is minus 1/2, right? So you have always combinations of these 2 guys, and they combine in such a way that always it's in that combination. So what we get at 3 loops, seeing that only these diagrams contribute, and these are called the rainbow diagrams, kind of a poetic, nice name, or sometimes ladder diagrams. Then if we assume that these diagrams, only these diagrams contribute, then at the next order we have the following. So let me erase. Right, that's a very good question. I will come back to that in a second. If you're looking at the planar theory, they can't. Yeah, but I will come back to that in a second. But that's a very good question. So now, at the next order, we get the following. We get now these factors that we would get before. Now we get this, but now we get the square of that. So lambda over 16 pi square right? Then we get now an integration contribution that is like dt1, dt2, dt3, dt4, but this one goes between 0 and 2 pi, this one goes between t1 and 2 pi, the next one goes between t2 and 2 pi, and the next one goes between t3 and 2 pi. And this is equal to 2 pi square to the fourth, sorry. Now can you tell me what is the factor here? Yes, 4 factorial. Very good. Because you are integrating on 1 over 4th, a 24th of the region. Very good. So, you get 1 over 4 factorial here. So it's 2 pi to the 4th over 4 factorial. And then we get a constant C2. Remember that in the computation of QED, what we had to see was the following. So if we have 4 gauge fields, A1, A2, A3, A4, or fields in general, we had to see the amount, the quantity of ways of weak contracting this. And this, in QED, it was 3, but now we have, if we are considering only the planar limit, the lines cannot cross themselves, so you have this choice, or you have A1 with A2, and then A3 with A4. So you have 2 choices. So this C2 is equal to 2. Let me be a little bit annoying, and let's put a C0, which is trivially equal to 1, and let's put a C1, that is the quantity of ways of contracting 2 fields, and this is equal to 1. Now, let's try to be more ambitious and bold, and let's say, okay, the computation at 3 loops is really, really hard. But let's assume that only rainbow diagrams contribute. If rainbow diagrams contribute, then this is equal, so at the next order, we have plus, now you understand the trend, 16 pi square cube 2 pi to the 6 over 6 factorial, and then C3, where these C3 are all the planar ways of contracting 6 fields. Can you tell me what that number is? So you can do it in your paper if you want. So basically, it's like a fun game, if you're a nerd. But it's 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So for instance, you have this one, right? This one and this one, right? But you could have this, this, and this. You could also have 1, 2, 3, 4, 5, 6. You could have, for instance, this one here, and these 2, like that. Then you could have, let's see if I am, yeah, well, it's just, I will finish. So can you tell me what is the number? So it's at least 3, but are there more? So you have the first with the, yeah, then the first with the last, but you can have this. And that's it. Yeah, and then the first 2, and you can have this. So in total there is 5. 5 different ways. So this C3 is equal to 5. Is that clear? You can try to find another one, but you won't. So this is 5. Now I am going to use the computer for a couple of minutes. So now what you do, well, either you are Zarembo and Simenov et al., and you kind of try to deduce this. But if you are lazy, you can actually do the following. you just come to this very nice web page, and it's the online, not games, encyclopedia of integer sequences, right? Maybe you knew that. And then you come here, and now we want to find a sequence that starts with 1, 1, 2, and 5, right? So we come here. It's very convenient, actually, for guessing things. It's 1, 1, 2, 5. Okay. And you hit search. It takes a little bit, but that's okay because I have a lot of time and not much to say. So. Oh, come on. Yeah. Okay, very good. The bad thing is that we got 1,340 series that start with these numbers. Now, if you are very lucky, and I am usually very lucky, you just get the first one, right? And you see that the first one is telling you that this Cn should be the Catalan numbers. So we come here, and we erase all that. So the first one is like nice. Actually, you could try to compute the number of ways to contract 8 fields, and you would find 14. That is the next term in the series. Now, what you see, this is very nice. This is telling you that this series is given by the Catalan numbers, and the Catalan numbers are 2n factorial over n factorial, n plus 1 factorial. So, we have, after our very bold assumption, right, but justified by this two-loop computation, we have, you know, like a prediction, or at least enough to write a paper. Like, you know. We cancel the factors of pi, and this is lambda over 4 to the n Cn over 2n factorial, where Cn is 2n factorial over n plus 1. It's just what I did there. So this is just, so we have a prediction, you know, this is our prediction for all values of lambda. So this is just 1 over n factorial, n plus 1 factorial. I will teach you another little trick. Now, if you don't have Mathematica in your computer, panic do not, because we have Wolfram alpha, right? Then you just go to Wolfram alpha, and we want to compute this sum. Sorry? Oh, no, I see, I will try that. Okay, so we have the sum of lambda over 4. I like Greek letters a lot, so I will write it in this way so the answer appears like lambda over 4 to the n divided n factorial and then n plus 1 factorial. Tac, tac, tac. N goes from 0 to infinity. Now I want function expand, so just it gives me the result in a nice way, unless if I did some mistakes. So it's computing very nice. So what Mathematica is telling me is that all this sum is equal to 2 times the Bessel function of a square root of lambda divided by a square root of lambda. And after our very bold assumption, this is what we got to all loops. What can we do now? Do you have some ideas? We try to see what happens for large lambda, right? Because we have computed this at large lambda. I haven't tried this. Yeah. Series to Bessel I imagine. 1, square, let's call it L. Just because I don't know if the notation that I am using is the correct one or not. Yeah, okay. So you see, the first one is 1 plus lambda over 8, so it's fine. Yeah, I just wanted to check. So now, but however, we don't want to do this, right? We want to do some infinite thing. Backspace, infinity, 0, and of course you will get all kind of crap. Yeah. And we see, yes. So you see from the first term that this goes with e to the minus square root of lambda times e to the 2 square root of lambda. So for very large values of lambda, this goes up to a factor with e to the square root of lambda. For lambda much larger than 1. And this was exactly what we have found with our strong coupling computation. So this is like a very big justification of what we have done. It's a test of the Eddy-CFT duality if you don't believe 100% in the Eddy-CFT duality as I do. So I see it more like a test of quantum field theory if you want. No, okay, so actually the way to prove this is by using localization techniques, but actually this computation was done much before all that, and it was actually one of the reasons that wanted to prove this result. This led to many works of modern works on localization. I think I will end here with these nice results. Thank you very much.
So are there any questions?
Yes.
So there are those rainbow diagrams. We assume that only those contribute. Have people actually shown that the other ones cancel in higher loops?
There are explicit computations at 2 loops. No, not by, as far as I know, no, not by explicit computation. But people has later found that actually this can be found by a matrix model. Actually, like the partition function of a given matrix model that is very famous is exactly that. So they have seen that the rainbows give all, so all the rest should cancel. But they haven't, I think, like computed everything. Yes, that's true. It comes from that too. But I didn't want to enter into that details, but yes.
Well,
yes.
Have people computed the power correction to the strong coupling behavior, namely the lambda to the minus 3/4 in this expression?
Like what? Yeah, I don't see why not. I think it's a very pretty simple computation. There are even non-planar corrections to all that you can compute. So the result is much more than that. Yeah, but I think there was a paper by Krunchensky and someone else computing 1 over square root of lambda corrections to that. Yes, and you can get that, yeah.
Are there any more questions?
What is the intuitive justification for this cancellation of diagrams, if any?
I can, in 2 minutes, I can explain you something interesting. In n equals 4 super Yanni-Mills, we have a lot of symmetries, right? These symmetries sometimes constrain the form of the loops. And it actually happens that there is a symmetry called, special conformal transformations that actually bring this circular Wilson loop into a straight line. And actually, to do the computation for the straight line is completely trivial. And actually, the expectation value for the straight line gives 1, identically 1. And actually, people can show that the difference between these two computations comes from a contribution that localizes in a single point. And that's why localization works, basically. So I think the intuitive reason is the fact that there is this transformation. And, well, I could explain a little bit more in private, and I mentioned something yesterday in the tutorials. But basically, this is one of the reasons. This is also the reason why the circular Wilson loop is so easy to compute. Now, diagrammatically, if you focus in like the non-rainbow diagrams, I think actually, if you focus in the rainbow diagrams and you have a look at them, they exactly mimic the computation of diagrams in this matrix model. So you expect that all the rest will give 0. So, yeah, I don't know if that is an answer, but yes?
If you do the same calculation on the CFT side, and you have rectangular ones.
Yeah, you could use your... Okay, so the question is whether...
You have to compare the factors and from, and you don't know the contribution.
Well, yeah, okay, so for the rectangular Wilson loop, things are very different, and people have tried to add up only this ladder for the rectangular, but it doesn't work. So it works only for this. It doesn't work. People have tried, there are other famous Wilson loops. Well, it doesn't work. You cannot use localization for the... Sorry? Yeah, you cannot.
And this is what causes the problem here, because you also can't identify the contributions.
Yes. Well, you could do a perturbative computation for the rectangular Wilson loop. It's just not very easy. You have to add up all the diagrams. And, yeah.
All right. Anyone else? If not, I think we should thank Fernando for his excellent lectures.
Thank you.